If you're serious about building robust AI applications, you've come to the right place. In this video, I'm gonna teach you everything you need to know about the MCP protocol as a software engineer. And in the upcoming videos of this series, we're gonna get our hands dirty in code and actually implement an AI agent leveraging the MCP technology. So let's dive right in. First of all, MCP stands for Model Context Protocol, and it's often compared to the USB technology because they're both open standards for connecting different systems to each other. You can connect a camera or a printer or any other device to your machine as long as this device implements the USB interface. Think about how powerful this is. Your machine doesn't need to know much about these devices beforehand, and they're even using the same port to connect. This is very similar to what MCP does. MCP connects LLMs to external systems, and your application needs to know very little about these external systems other than the fact that those servers actually conform to the MCP protocol. So integrating new tools to your AI app becomes as simple as connecting a device to your machine using your USB port. That's how powerful this protocol is. All right, so let's make things a bit more concrete. MCP being a protocol, it means it's just a set of rules. It's a convention. The MCP specification is just a text defining how client and server should behave and interact with each other. That's all. No code at all. Of course, you can have MCP implementations in different languages, like you have a Python SDK, Java SDK, and much more. So it's basically this standard for connecting AI to external systems, given that LLMs, when they're operating on their own, they can't do much other than generate text. And the problem this protocol solves is the problem of creating different custom integrations to different systems. So before MCP, you had to actually integrate your application to different systems, and this was expensive and time taken. But with MCP, you actually have this lightweight layer that translates the LLM requests to these external systems, and it becomes very simple to leverage tools in your AI apps. Maybe you've been connecting tools to your LLMs before the MCP protocol even came out. It's totally possible to do so. But let me tell you why I think you should follow this protocol going forward. This standard makes it very easy for you to leverage open source code rather than developing your own custom integrations from scratch. Let's suppose you want to integrate MongoDB to your AI app, giving your LLM access to executing some operations in your database. You could always develop this custom integration from scratch, but that would be costly and time consuming. Rather, what you can do, you just go to GitHub and you grab the official MCP server by Mongo, and you just add an entry for that server in your config.json file, a file that holds all of your MCP servers. And even though your application knows very little about this external system, it knows one very important thing. It knows that this external system implements the MCP protocol. So it knows how to request for listing the tools available and also for executing those tools, what arguments it takes. So as long as you have implemented your app to follow the MCP standard, it becomes very easy and fast to integrate new tools, leveraging code that other people have already built in the past. So that's why I think following the MCP protocol is very important. So let's dive into the typical flow of an AI app. Usually the user makes the first move, asking for a task to be executed or asks a question. The LLM decides whether or not to call an external tool. And once that tool returns, the response is incorporated into the LLM context so that it can generate the final answer to the user. This loop is usually implemented by AI agent frameworks. And the MCP protocol lies right here. It's a communication layer. So remember, LLMs can only generate text. So when we say an LLM is calling a tool, basically it's just generating a specially formatted text, often JSON, and your code actually parses that JSON and calls the tool on behalf of the LLM. Also, in part 2 of this video series, we're going to implement this main loop and from scratch without using any agent frameworks, and it's going to be very valuable for you to understand how this thing actually works under the hood. Let's now talk about the three main actors of the protocol. First, we have the host, which is the AI-powered app. For instance, IDEs like Cursor, IDE extensions like GitHub Copilot and Cloud for Desktop, they're all hosts. If you're working on an AI app, your AI app is probably a host too. Then we have the MCP client, which is just a connector that knows how to communicate with the MCP server following the protocol. In terms of code, the client is usually just an object in your application. So we import a class using whatever SDK library you're using for MCP and instantiate that class. And finally, we have the MCP server, which is a standalone program that could be running either locally in your machine or remotely. It's a simple, lightweight program that knows how to interact with the external system. It could be like a database or a REST API. It simply translates the client requests so that it can interact successfully with those tools. And this is what the overall architecture looks like. We have here your local machine, which is running the host application. Your code is really doing most of the heavy lifting. It controls when and whether to call the AI model, when to call the MCP client, when to call tools. The AI model could be running either locally or remotely, doesn't matter. In this example, we have an MCP client which is connecting to a remote server, which could be, let's suppose, an official server from the Slack team. It's also connecting to a locally running MCP server, which exposes functionality related to your local file system or a Postgres database. Notice how the MCP protocol, it kind of represents a small piece of this entire picture. I'm saying this to tell you that the MCP protocol is not going to solve all of our problems. It solves some of the problems, but there's still a lot of hard work to be done here, all right? One more caveat. So we cannot have a single MCP client connecting to multiple MCP servers. They actually hold a one-to-one relationship. So for each MCP server that we want to connect to, we should instantiate a new MCP client. The protocol is under active development, so we should expect to see an incoming flow of improvements in the following months. Just a few weeks ago, in March 26th, they have added support for authorization, which before was not baked into the protocol. They have made some changes to the transport, which we're going to cover later in this video. They also added JSON RPC batching and some other features as well. So now let's talk a little bit about the types of messages that are exchanged between the server and the client. The first type is the request, which must have a unique ID for the session. And notice that either a client could send a request to the server, but also a server could send a request to a client. And this is also true for the other messages as well. And this is what the interface for the request looks like. We have the JSON RPC protocol version, the ID of the request, the method, which is a string that uniquely identifies each operation. For instance, listing the available tools is one operation, calling a tool is another operation. We can optionally pass in a progress token, which allows us to receive later on updates from the server or from the client regarding how far along it has progressed. I'm going to show you an example of this in a little bit. To make things a bit more concrete, let's look at a tool call request. So we have the JSON RPC version, the ID. We have the method, which uniquely identifies this tool calling operation. You're going to notice later that all the other operations follow a similar naming convention for the method. This is all defined in the protocol itself. We're sending a progress token because we want to learn about the progress that the server will make towards getting the weather forecast of these cities, all right? Once the server or the client has a response for the request, it's gonna send a message, a response message, carrying the same ID to the corresponding request. So the interface looks something like this. We have result and we have error. And the concrete example could be like this one. We're gonna get the weather forecast for each of the cities that we have requested. And then finally, we have the notification message type. It does not expect a response. It just expects the recipient to acknowledge using a 2HU accepted. The notifications do not include an ID, and they could also go either way, either client to server or server to client. The interface looks like this. It's pretty simple. And a concrete example would be progress notification. So in this case, we're getting the same progress token that we had emitted before. And we know that the server has already processed 2 out of the 3 cities that we have requested. So with this kind of feature, we can provide our users with like loading bars and give them a sense of how long it's going to take for their requests to get fulfilled. Let's now talk about client features. The first one being sampling, which is one of the most important features of the protocol. It basically allows servers to request clients for AI completions. And the reason this is so important is because the MCP client and the host application actually retain control of what data is being exposed, and also AI, which LLM specifically is getting the requests. So you can easily integrate a new MCP server into your application because you don't need an API key to expose AI to this MCP server, and you have a better control of privacy and security using this architecture. Please notice that despite the advantages of this feature, we have to be careful of attacks. We should implement some sort of rate limiting, and we should only integrate MCP servers that we do trust into our applications. So this is what the sampling request message looks like. We have the method sampling/rate message. We have the list of exchanged messages. In this case, we have just one message from the user asking what's the capital of France. The server is providing some preferences. It would like to use the Claude 3, so an A family of models. But if you cannot use this model specifically, the client, it doesn't have to follow. It should prioritize intelligence. See that this one has the highest score. The second priority should be speed, and third, cost. The client is not obligated to follow any of these instructions. It can implement sampling in whatever way it wants. Actually, it's not even obligated to implement sampling at all. So during the initial interaction between client and server, the session initialization, the client can tell the server that it does or does not have sampling capabilities. Next, we have routes, which is a really simple concept. It's just a way for the client to let the server know which is the root directory it should operate on. So the typical flow of this is the application asks the user for a input directory, and the client will let the server know which routes are okay to interact with. Notice that although the server should comply with the routes specification, there are no guarantees. So once again, we should be mindful of which MCP servers we are interacting with. An example is an app that refactors our code base. The client can let the server know what's the root directory it should operate on. There's also a special message type, which is a notification that the server can learn about any changes to the list of routes. There's also similar notification for tools and resources, which we're going to cover in a little bit. Now let's move on to server features. The first one being prompts. So prompts are just templates that are available to be used by the client and the host application. They are meant to be user controlled, so the user chooses when and whether to use these prompts. So for instance, if you're using GitHub Copilot, when you type something like /fix or /tests, the application is injecting a prompt that will enhance the behavior of the LLM under the hood. The most important operations, the methods, are prompts list, prompts get, which accepts some variables so that you can replace those variables at runtime. Basically, the server is rendering this prompt. And then notification related to the any changes in the list of available prompts. Besides text, it also supports image and audio in the prompt, which is really interesting. Second, we have resources. The most common example of resources are files, database schemas, and documentations. The resources are meant to be application controlled, so the host application is choosing when and how to incorporate this context into the LLM's prompt. The best example of this would be a application that interacts with a database. So whenever the user requests a read or modify query, the host application would automatically include the database schema to the prompt because it's a very important information for the LLM. Notice these rules are not written in stone. So for instance, this is cursor, where you can explicitly include files or documentations into your prompts. This is very much user controlled rather than application controlled, and that's fine. You have freedom to make some choices in your application, and you don't have to strictly follow every detail of the protocol. We're going to look at tools next, but there are some similarities between tools and resources. But let me highlight some key differences here. Resources are meant to target a very specific piece of data, and resources are not meant to be controlled by the model. The most important methods here are resources list for listing the available resources, resources read for reading the content of a specific resource, notifications resources list changed, which notifies the client that a new resource has been added or an existing resource has been removed. And then finally, we have resources subscribe, which is really powerful. So let's suppose you're using a database schema resource. If this database schema changes over time, the client has to know about it. So the client can subscribe with the server to a very specific resource and learn about any changes that happen to that resource over time. The third and most exciting capability of the server is tools. So tools are designed to be model controlled. So the LLM chooses when and how to use these tools. So their usage is not deterministic. The most common operations here are listing the tools, calling a tool, and getting notifications related to any changes to the list of available tools. I know that sometimes differentiating between resources, prompts, and tools can get confusing. So I brought this example of an MCP server that interacts with the database. Notice how they have defined each of these capabilities. First, we have resources. We have one resource which simply returns the entire schema of the database. Then we have tools, which are mainly for running SQL queries against the database. And then finally, we have prompts, which are just templates that are injected into your interaction with the LLM. So for instance, explain query. Rather than you having to type out for the LLM that it's supposed to explain the query, you can just slash explain query, and then you're going to get for free a optimized prompt that tells the LLM how to behave. And it's much faster and provides a better user experience. Now let's move on to transports, which is the channel of communication between the client and the server. So if you're running your MCP server locally, you can use standard I/O to communicate. In fact, you should use standard I/O because it's the simplest and most efficient transport available. In this situation, usually the client will launch the MCP server as a sub-process. The client just needs to know what's the command it's supposed to run to launch the MCP server. And then the client will have access to standard input and the standard output of the sub-process, and that's what's used for communication. So whenever the client writes to standard in, the MCP server is going to read the message from the client. And whenever the MCP server writes to its standard out, the MCP client will read the server's message. So the underlying mechanism that supports this transport is message passing inter-process communication. Despite the complicated name, this is very simple and it's a built-in functionality of the operating system. So when you're using pipes to run commands in your terminal, that's exactly the same thing that happens. Basically, you're taking the standard output of one program and writing to the standard input into the next one. So before we move on to the second and last transport, let me give you a quick refresher on what is SSE. So SSE stands for Server Sent Events. It's a unidirectional long-lived HTTP connection. Okay, this is a mouthful, but let me put it in simpler words. It's basically a connection that allows the server to send messages to the client at any time as long as this connection is open. So usually when we're talking about web, it's the client that is reaching out to the server and the server is simply responding to the requests from the client. But in the MCP protocol, we actually need the server to be able to send requests to the client and then receive a response back. So the way the MCP protocol implements this is using server sent events. Now we can talk about streamable HTTP, which is the second transport. You should definitely use this transport if you're connecting to a remote MCP server. Now I'm going to walk you through a typical communication flow between the client and the server. So the first thing that happens is the session initialization. So the client and the server, they negotiate the protocol version. They tell each other which capabilities they have. So the client tells the server whether it has routes and sampling capabilities, and the server tells the client whether it has tools, resources, and prompts capabilities. And this information has to be stored somewhere for the upcoming requests in the future, which means that this connection is not stateless like REST. This is actually a stateful connection. And that's why in here, the protocol defines the session ID. So it can store all of this information with a unique identifier attached to the session. And the first thing the client should do is sending a GET request to the MCP server. So the server has the opportunity to open the SSE connection. And once this connection is open, it can send requests and notifications back to the client. So for instance, notifications could include like changes in the list of available tools or changes in the list of available resources. Then the client will start sending request messages to the server using the post HTTP method. And the server has the option to either return immediately or open a SSE connection. It's yet another connection. And while this connection is open, it can send requests and notifications related to the original request. So things like progress notifications or completion requests, which is sampling, what we have seen before. And then finally, the server will send its final response and close the SSE connection. Notice the server has closed this SSE connection and not the original one, which remains open. And for other requests, maybe the server this time decides not to open an SSE and just return the final response immediately. Your client has to support both situations. Congratulations for watching all the way to the end. We've covered a lot of ground and we've laid the foundation which we're going to build upon in the upcoming videos of this series, where we're going to build the host application, MCP servers, MCP clients, all of that in practice. If you want to keep learning and do not miss on the upcoming videos of this series and the other series which I'm making, subscribe to this channel. And if you've learned something from this video, please leave your like. It really helps me and supports my work. Please leave any questions that you may have in the comment section below, and I will make sure to answer all of your questions. Thank you guys and keep learning.